to the section on modeling. This is one of my favorite sections. Today we're going to talk in particular about mixing and cooling. So here I've got a guiding principle for mixing problems for you, and you can read through that as I'm going through a problem and make sense of what I'm doing in terms of that image. So let's just jump right into a problem. We've got brine going into a tank, getting mixed around, and then leaving. I'm going to let A of t be the amount of salt in the tank at time t. And so let's set up a differential equation for the rate of salt in tank at time t. The rate in, concentration of salt going in, well, that's 0.05 kilograms per liter. You don't have to put the units on here when you're setting this up, but I'm doing this to show you how the units cancel and then you get the units you want. The input rate of the brine is going in at 6 liters per minute. So the liters are canceling and we're getting kilograms per minute as our rate going in, and that makes sense. And 6 times 0.05 is 0.3. So 0.3, and I'll just leave the units off there. Okay, rate out. Concentration of the substance leaving. Well, this is going to be the amount of salt in the tank, which is A by supposition, divided by the volume of the tank. All right, well, what is the volume of the tank? Let's go over here. The volume of the tank, it's 50 liters, because it initially holds 50 liters of brine. We're told that, 50 liters. And then every minute, 6 liters comes in. So plus 6t. But then every minute 6 liters goes out, so that's minus 6t. So the volume of our tank is constant at 50. So A over 50. The units here are kilograms per liter, and it's leaving 6 liters per minute. And so we get 3 over 25 times A. All right, now our differential equation, dA dt, the rate, is equal to rate in minus rate out. So again, rate in minus rate out. Rate in is 0.3. Rate out is 3 over 25a. Let's write that in standard form for a linear differential equation because it is linear. This is dA dt plus 3 over 25a equals 0.3. And the initial condition is A of 0 equals, and then we have to go back and read the problem. The tank initially holds 0.5 kilograms of salt, so 0.5. So this is our setup. It's an initial value problem, and we want to solve it to find out how much salt is in the tank at any time. So I'm going to solve this as a linear differential equation. My P of t is 3 over 25, and my Q of t is 0.3. So the first thing we need is an integrating factor. Mu is e to the integral of 3 over 25 dt, which is e to the 3 over 25t. So then we jump to the magical step. Mu times a, so e to the 3 over 25t times a, my variable's a, not y, is the integral of mu q. Q is 0.3, and mu is e to the 3 over 25 t dt. Okay, well, when I integrate, that's 2.5 e to the 3 over 25 t plus a constant. Divide both sides by mu over here to get a equals 2.5 plus ce to the negative 3 over 25t. All right, we're almost done. Now we just need to find c. Find c by using a of 0 is 0.5. So 0.5 equals 2.5 plus c, e to the 0 is 1. So this gives us c is negative 2. So our final answer for the amount of salt in the tank at time t is 2.5 kilograms minus 2, because c is negative, e to the negative 3 over 25t. And there we go. Okay, let's do another setup and solution, which is a little more difficult. Here, the volume of the tank is not constant, but we're going to solve it same way. So I'm going to start with rate in and rate out. So rate in, the concentration is 2 pounds per gallon. So 2 pounds per gallon times 3 gallons per minute. So 6. And the units are pounds per minute. That makes sense. Rate out, I want the concentration times the rate it's leaving. It's leaving at 2 gallons per minute. For the concentration, that will be the amount of salt in the tank divided by the volume of the tank. So we need to go over here and do the volume of the tank. The volume is 400 gallons plus 3T. I'll just leave the gallons off this, it's confusing. 400 plus 3T minus 2T. So that's 400 plus T. Every minute you're gaining a gallon. So 400 plus T. So when I multiply that, I get 2 over 400 plus T all times A. Okay, so dA dt is rate in minus rate out. Rate in is 6. Rate out is 2 over 400 plus T times A. Let's write that in standard form because it's linear. dA dt plus 2 over 400 plus T times A equals 6. And A of 0 equals, and we have to go back and read the problem, the tank initially holds 400 gallons of pure water. That's 0 kilograms of salt or pounds, whatever units we're using. All right, okay, so this is our setup. Now we solve. It's linear. Mu is e to the integral of 2 over 400 plus T dt, which is e to the 2 ln absolute 400 plus T. Bring that 2 up as an exponent, and that's 400 plus T quantity squared. So our magical step is 400 plus T quantity squared times A equals the integral of mu q. And q is 6, so 6 times 400 plus T, you should write smaller than I am, squared dt, which is, let's see, 2 times 400 plus T, 400 plus T cubed plus C. So divide both sides by 400 plus T squared, and we get A is 2 times 400 plus T plus C divided by 400 plus T squared. Okay, now your job, use the initial condition A of 0 equals 0 to show that C turns out to be negative 128 million. And so your final answer is in the box here. So you can see that if the volume is constant or if the volume is not constant, you're going to solve the problem the same way, set it up the same way. It's just a little more difficult to solve if the volume is not constant. So here's a practice problem for you, and you're not going to solve it. I just want you to do setup, and you're going to set it up for part A, the volume is constant, and for part B, the volume is not constant. And in each case, I want you to state the initial conditions. The solution is on the last page, so I'm just going to trust that you do that. Okay, Newton's law of cooling. Here it is. K is a constant, M is the temperature of the medium, T is the temperature of the object. So let's just jump right in with an example. A cold beverage of your choice is initially at 35 degrees and warms up to 40 degrees in 3 minutes. The temperature of the room is 70. Find the temperature of the beverage. Okay, so what are we given? I always like to write down the information I'm given in terms of equations. I'm given that T of 0 is 35. I'm given that T of 3 minutes is 40. And I'm given that M the temperature of the medium is 70 degrees. So my differential equation is d big T d little t. I'm going right from this equation here, plugging in what I know, is K times M, which is 70 minus big T. I want to solve that for big T. I'm going to separate the variables. Okay, so I'm going to bring the 70 minus big T to the left. 1 over 70 minus big T. D big T is K, which is constant, d little t. Integrate, integrate. All right, on the left, I get, do a U sub in your head, but be careful. There's a negative in front of that big T. So negative ln absolute 70 minus big T. And on the right, I get K little t plus a constant C. I could move this negative up as an exponent, but I don't want to do that. It's much easier to just move the negative over to the other side. Ln 70 minus big T in absolute value is negative KT plus negative C. I'll just call that B. It's another constant. Okay, now exponentiate both sides. And you can remove the absolute value the way we've been doing. So this is going to give us 70 minus big T is another constant A e to the negative KT. And that A is sucking up the plus minus in my absolute value. All right, so now let's solve for T. Big T is 70 minus A e to the negative KT. So that's hurdle 1. We've gotten this far. Kudos to us. We've gotten big T. There's only 2 constants we don't know, A and K. So we need to find those. The first one we're going to find is A. So we're going to use the fact that T of 0 is 35 to find A. So 35, you should write small, is 70 minus A e to the 0 is 1. So that tells me that A is 35. So now T is 70 minus 35 e to the negative KT. That's hurdle 2. So now we're going to find K. So I'm going to come up here and use T of 3 is 40 degrees to find K. So on the right, I have 40. That's the left, actually. And 70 minus 35 e to the negative 3k. Need to solve for k. So I'm going to subtract 70 from both sides to get negative 30 and divide by negative 35. So on this side, I'll have 30 over 35. And on this side, I'll have e to the negative 3k. Now, 30 over 35 is 6 over 7. Pause if you didn't follow that. Now I can take ln of both sides, and I get negative 3k, I'm switching sides here, is ln of 6 over 7, which implies k is negative 1/3 ln of 6 over 7. Perfect, now we're done. So the important thing to keep in mind when you write down your final answer, big T of little t, k is negative here, and coming back over here to hurdle 2, notice that there's a negative in front of the k. So we need to incorporate that. Since k is negative, this will turn out to be positive. So big T is 70 minus 35 e to the positive 1/3 ln of 6 over 7, and that's all times T. And that gives us the temperature of our beverage at any time. And that is the end of this section.